copper is also coordinated by an equatorial and axial water molecule when docked onto the substrate. And we can see when the substrate comes on, the axial water molecule will need to be displaced in order to make room for the substrate. This activates the cover, and we can see that in many of our structures, a chloride atom is present in the active site, sort of as an oxygen mimic, placed fairly close to the C1 and C4 positions where it would find its application. Compared to glycoside hydrolases, the LVMOs act very gently on their substrates. As you can see, for an LPMO over here, there's very little torsion, twisting, bending, and also that on the substrate. Whereas I just picked a random example from the PDB, where you see a lot of bending and twisting motion in the substrate in the active site. So far, LPMOs have been classified in the carbohydrate active enzyme database as auxiliary activity enzymes 9, 10, 11, 13, 14, and 15, all sharing the common immunoglobulin fold and all sharing the histidine brace motif. Some of the families have fungal origin, some bacterial and viral, and most recently a insect origin was also found. Some of you may have noticed that some of the fungal histidine braces has this little post-translational modification of a methylated histidine, which is quite unusual, and the exact function of has yet to be determined. So this project was on two fungal LPMOs, both from the AA9 family, one from Lentinus similis and the other from Collaria virescens. These two, oh nice, it's working. These two structures, enzymes share a sequence similarity of 46% and a C-alpha RMSD of 0.6 angstrom. So in terms of structure, they are fairly similar, and they are active on largely many of the same sort of substrates. So we were, of course, interested in seeing if there are any clear differences between how they bind or interact with these substrates. Shown here is a paste gel from on the left with the celotetraose with the LS CV variant, the LS variant cleaving right down the middle of the substrate, producing celobiose, with the CV variant producing celotriose. So that sort of gave us an indication that there are actually differences in how they act on the substrate. For cyto-oligosaccharides, it's even more clear. The LS variant of the enzyme was very active on cyto-oligosaccharides, with the CV variant being hardly visible. So anyway, we did our soaking experiment by first transferring the crystal into a catalytically relevant pH of 5.5 and then moving it again to similar conditions, but also containing the substrate of interest. First off, we got the celotetraose complex. You see the substrate is positioned nicely into the electron density from the -2 to +2 subsites. We were able to identify various hydrogen bonding at the active site surface, and sort of give us a good foundation to study the interactions. Further on, we have the celopentose complex structure we got, sort of evolving forward from the celotetraose. We have now also the -3 subsite involved, not involved in any hydrogen bonding, but instead an sort of aromatic stacking interaction with a tyrosine. Growing the substrate even further, we see the -4 subsite now being involved as well. So our hypothesis is that the +2 subsite is really the most sort of relevant position for at least these shorter substrates. For the CV variant, we were initially not able to get complex structures, and one thought on this was that the +2 subsite was comprised of rather different amino acids. So at least very short substrates like cellotriose would not be able to bind. Eventually we tried cellotetraose, and we got a very nice structure placed perfectly into the electron density. But compared to the LS variant, which bound from -2 to +2, you now see binding from -3 to +1, which corresponds nicely to the activity profiles. It was only later that we also found out that the crystal form for this new complex was rather different than our previous one, just down here, which gave us further complications when trying to get a cellopentanone structure, which was again in the initial crystal form, all from the same conditions, by the way. So what we were able to see in structures from crystal soap in cellopentanose was really only a cellotriose, so the two remaining subsites were more or less invisible. A further thought on this, other than the crystal packing being different, was that the interactions at the +1 subsite over the methylated histidine was not strong enough to keep the substrate on to the active site. And we did a little search in the literature on this, and found that there are not that many oxygen to histidine ring interactions in the PDB or in the CFD for that matter. By now, most of them are from already solved complex structures of LPMOs. So we thought that this might be a too weak interaction to sort of keep those onto the surface, at least for the CV structure. So what might be happening is just that it's flopping around a bit, making it invisible to the electron density. But if we grew the substrate further and did a cellohexo soak, we saw that placed rather nicely in the active site. Superimposed with the substrates from cellotetraose and cellopentanose, we see that they fit rather nicely together, but we have sort of more involvement with the amino acids in the +2 and now also +3 subsite regions. So comparing the LS variant with the CD variant, we see that the hydrogen bond pattern is rather different. And that might have some mechanistic implications for the enzyme, which has to be really fully unraveled. As mentioned a couple of slides ago now, the LS variant was also active on cyclo-oligosaccharides. So we tried to, of course, sort that into our crystals as well. And compared to the cello-oligosaccharide structures we got, this was rather different. You see the +1 region that would, for cello-oligosaccharides, be placed flat onto the active site surface. Now we have sort of a 90-degree rotation for this xylose monomer, really giving an indication that there might be something different going on here. Additionally, we see the chloride oxygen mimic being positioned at the axial position instead of the equatorial position, which is quite peculiar. And lastly, the cello-oligosaccharides chain is sort of translated half a Pyrenees unit, if that can be defined as a unit of length, towards the non-reducing end of the polymer, really giving an indication and proof that there is something different going on in terms of mechanism, and promises a lot of new work to blossom from these studies. With that, I would like to end my presentation, and I hope I have sort of given you an idea that we have elucidated these structural features of the enzyme-carbohydrate interactions, and that these subtle differences really do have a lot of importance in terms of substrate cleavage. If you want to know more about LPMOs, there are now a bunch of reviews in the literature, so I urge you to pick one and if you're